In the previous video, we reviewed the concept of linear dependence and independence. Now, linear independence cannot always easily be determined, especially when we are considering more than two functions. In this video, a useful tool to evaluate linear independence will be presented. So recall that if we have two functions, y1 and y2, then we say that these two functions are linearly independent on an interval if that equation is only satisfied if c1 and c2 are both equal to 0. That is, we cannot tune c1 and c2 and find the right combination thereof and set that equality to 0. So let's try to formalize this a bit more. So we're going to start with that statement of c1 y1 plus c2 y2 is equal to 0. And what we're going to do, we're going to take the derivative of this equation with respect to x. So this forms a system of two equations for two unknowns. Now let's say we wanted to eliminate c2 from these equations. So what we would do, we would multiply the second equation by y2 and the first equation by y2 prime. And what that would lead us to is c1 y1 y2 prime minus y1 prime y2 is equal to 0. And this is obtained, as I said, by multiplying equation 1 by y2 prime and equation 2 by y2 and subtracting the 2. Now, if you want to check this for yourself, please go ahead and pause the video and try to work this out for yourself. So we're going to set this equation as equation 1. Now let's say we wanted to eliminate c1. So in this case, what we would do is multiply equation 1 by y1 prime and equation 2 by y1. And then subtracting the 2 to get rid of c1, we would find that we have c2 multiplied by y1 y2 prime minus y1 prime y2 is equal to 0. And this we will call equation 2. Now notice that the bracketed term in both equations is the same. If this factor is not 0, then the only way these two equations can be satisfied is if c1 is equal to c2 and both of these are equal to 0. So this factor in the brackets can be expressed in determinant form as y1, y2, and then y1 prime, y2 prime, and this is equal to y1, y2 prime minus y1 prime, y2. And this function, which we denote as w, is called the Wronskian. So with the help of the Wronskian, we can say that two functions are linearly dependent in an interval if their Wronskian is 0 in that interval for all x. So we write that out here. Again, two functions are linearly dependent in an interval if their Wronskian is 0 in that interval for all x. We can extend this concept to more than two functions y1 and y2. So we can say that the Wronskian of n functions, y1, y2, all the way to yn, is equal to, and so what I'll do here is just move this down a bit, so we can write this out properly, is equal to the determinant of y1, y2, all the way to yn, and then we have the first derivative of these n functions, and then all the way to y1 n minus 1, y2 n minus 1, all the way to y n minus 1. So having extended the concept of the Wronskian for n functions, we say that these n functions are linearly independent if the Wronskian of these n functions is not equal to 0 on that interval. And therefore, the only way we can make that linear combination equal to 0 is for the constants c1 to cn to be equal to 0. And we say that n functions are linearly dependent if their Wronskian is equal to 0 for all x in the interval.